Jieming. Presenting this paper, it's a joint work with Santiago, Yuan, Vahab, and so on. So this paper is motivated by the growing adoption of automated bidding. You might have heard of auto bidding in some other talks or the auto bidding workshop. Just to give you some background, automated bidders are bidding products that allow an advertiser to only specify some very high-level goal after setting up conversion tracking. It is much simpler to use compared to manually bidding on different keywords. Here is a screenshot from some Google external page. As you can see, there are two auto bidding types here, target CPA and target ROAS. They are basically maximizing the number of conversions or conversion value subject to some target constraint. For example, for target CPA, there's an upper bound on the cost per conversion, meaning the total payment divided by the total number of conversions. Okay. And I want to mention that in recent years, there's a good amount of work studying auto bidding from different angles. Do I need to get them? Do I need to get them? No. Okay. And there's also a very recent CECOM survey on the auto bidding. So in prior work, auto bidding are usually modeled as value maximizers. A value maximizer basically maximizes its total value. You can think it as clicks or conversions subject to some return on spend constraint. The constraint is basically saying the total value should be at least some target times the total payment. If you compare a value maximizer to the standard quasi-linear utility maximizers, you will see they are quite different. And results for utility maximizers may not work for value maximizers. So now we have these value maximizers as an abstraction of the auto bidding. How about the advertisers who use auto bidders? It's a longer discussion about whether they are also value maximizers or they're just using auto bidding as a tool to optimize some other objectives. I'm not going to cover it in this talk. In this paper, we're just assuming they're also value maximizers, and we don't really distinguish between the advertiser and the auto bidder. So we consider them as a single entity, the buyer. So here's our problem setup. We have a seller, you can think that's an advertising platform, sells a single item to the buyer, and there's some production cost C if the item is sold. And the seller's objective is to optimize profit, which is payment minus cost. And the buyer, you can think it as the advertiser, just a value maximizer with a return on spend constraint defined in the previous slides. Notice here that the buyer has two important parameters. One is its value, and another one is its target. So if we look at the buyer's information structure in this paper, we consider Bayesian setup, and we assume the value and target are sampled from two independent distributions. And in this paper, we assume the value and target are private to the seller. There's a very relevant prior work, our EC'21 paper. It shows that if one of the value or the target is public, then the first best is achievable, and we can characterize the optimal auction. The first best here means the optimal profit if the seller knows the private information of the buyer. And that EC'21 paper also shows that if both the value and the target are private, then the first best is not achievable. And in this paper, we try to characterize the optimal mechanism in this private setting in the case with a single buyer. So here's some more details about our problem setup in terms of timing of the events. In the first step, the buyer draws its target from a distribution and sends some message to the seller. In the second step, buyer draws its value from another distribution and send another message. In the end, the seller decides the allocation and payment deterministically based on both messages, according to some mechanism it commits to. And in this paper, we try to characterize the optimal mechanism for the seller. And in particular, we'll try to answer this question, whether M1 is necessary for seller's profit optimal mechanism. Notice that here M1 is sent after the target is drawn and before the value is drawn. So it's basically used as screening targets. So the first step we did to characterize the seller's optimal mechanism is to make the seller's mechanism more direct. So by an argument like the taxation principle, we show that the setup in the previous slides can be implemented as some setup here. So in this new setup, the seller offers a menu of two-part tariffs. Here, a two-part tariff is basically two numbers. One is the fixed unit price, and another one is the entry fee. In the second step, the buyer draws its target from the distribution and picks a manual item and pays some entry fee. In the third step, the buyer draws a value and purchases the item with some probability. So this will be the model we mainly work with. So here's our main result. We show that the optimal mechanism does not require target screening. In other words, offering a single two-part tariff is optimal for the seller. We also call this single two-part tariff linear pricing. It will be more clear when we get to later part of the talk, why it's called linear pricing. In addition, we also show that this two-part tariff has a negative entry fee, meaning in the seller's optimal mechanism, the seller will first offer a lump sum subsidy to the buyer and then charge a fixed unit price. In the rest of the presentation, I'm going to talk about the proofs. There's three major steps. In the first step, we reformulate the problem a bit more in addition to the two-part tariff formulation. In particular, we focus on a key quantity, which is the buyer's expected purchase probability. And we put other quantities like seller's pricing function as a function of this quantity. In the second step, we adjust the seller's pricing function a little bit to satisfy a single crossing property that can greatly simplify the proof in the third step. And that adjustment doesn't change the outcome of the mechanism. And the third step, which is the most involved step, we prove the optimality of the linear pricing of the no target screening based on some geometric understanding of the problem. So let's start with the problem reformulation. And we can go back to this two-part tariff setup. So we first look at the step 3. And we try to simplify the buyer's decision in step 3 into a single quantity, which is the expected purchase probability Q. And if you look at this, and if you think about the case when the buyer fixed the purchase probability Q, then the buyer's decision in step 3 is pretty simple. Basically, the buyer will just greedily pick items with higher value. Or in other words, the buyer will basically buy the items if the item's value is the top Q fraction of the distribution. So the purchase probability Q of the buyer will decide the buyer's decision in step 3. And that will also determine the allocation and the value of the buyer, no matter what happens in the first two steps. So the buyer's purchase probability Q will decide the value, and we can write down it as the value function U of Q. It's not hard to see that this U of Q function is concave because when we increase the purchase probability, the marginal gain value will be decreasing. Good. Next, we can look at the step 2 and think about situation when we fix the purchase probability. So notice that now the value is fixed. What the buyer can do is only to decrease the payment so that it's easier to satisfy the target constraint. The buyer just want to pick the manual item to minimize the payment. And the payment is basically the entry fee B plus the unit price A times the purchase probability Q. And we can write down this pricing function P of Q. And notice that it's also a concave function because it's basically the infimum of a bunch of linear functions. Right? So here I want to show that if buyer decides the purchase probability after the target is drawn, the later decision are pretty straightforward. And we have these two functions, value function and pricing function. So now how should the buyer pick the purchase probability? We can just use the value maximization definition, maximize the value, which is the function we just defined, subject to that the value is at least tau times the payment. On the right, we have some visual version of this optimization. It's pretty simple optimization. We have two curves. One is a pricing curve, this blue curve, P of Q. And another one is the value curve, U of Q, divided by tau. And this buyer's best response is basically picking the largest Q such that the pricing curve is still below the value curve. And usually this Q will be at the crossing point unless we go to the boundary Q equals 1. So finally, the seller's optimization just can be considered as designing the pricing function P of Q that is concave. And the goal is to maximize the expected profit. The profit for particular tau is just this formula, and it's basically depending on the purchase probability, which related to the crossing point on the figure. I want to define one additional quantity before I get to the main intuition. Which is the first best benchmark, and I want to create another curve. So if you're familiar with the value maximization, the first best is pretty simple. It basically the seller just sells the item to the buyer if the value over target is above the cost, and at the price value over the target. And for the first best mechanism, we can also get its pricing curve. And with some mild assumptions, we show that it's strictly convex. So finally, we can get to some intuition of our main proof. We put all the three curves we defined previously. The red curve is the first best payment function. The blue curve is the pricing function. The pricing function is concave. The first best is convex, strictly convex. And there's also another value function, U of Q divided by tau. For this value function, you should think that there are many scaled versions of it depending on the target. And the crossing point here between the value function and the other two curves gives you the purchase probability of the seller's mechanism and the purchase probability in the first best. So from this figure, you can get some intuition why the first best is not achievable. Basically because the first best curve is strictly convex and the pricing curve is concave, so they cannot agree on all points. And from that, you will have some idea why we think the linear pricing is optimal. And we show this proposition. Basically, for any concave pricing curve, the blue curve, we can show there exists a linear pricing function whose purchase probability is closer to the first best. So in this figure, this linear line will be the line going over the two crossing points of the red and blue curve. And it looks like it's closer to the red curve. And finally, why do we care about being closer to the first best? We have a lemma showing that if the purchase probabilities move closer to the first best, it means higher profit. So with that, we can show that for every pricing function, P of Q, there exists a linear pricing function that is weakly better in terms of profit. So this is the main intuition of the proof. Now to get a formal proof, I want to show there's some non-trivial efforts need to be done. First, there are actually 5 different cases depending on the number of crossing points of the blue and red curves and also their positions. In the first case, there are 2 crossing points, similar as the figure I showed earlier. In the second and third case, there's only 1 crossing point. And in case 2 is on the top, in the case 3 is at the bottom. These 2 cases are not symmetric because there's slightly different properties we want to use on the first best and the pricing function. And the last 2 cases, there are no crossing points. In each of the case, we need to pick a straight line and formally show that the crossing point between the value function and the linear function is in between the other 2 crossing points. And to get the proof, we use a lot the intermediate value theorem and some convexity and concavity of the curves. Finally, I want to briefly mention why we need the auxiliary pricing function. The main reason is that the pricing function and the value function both are concave curves, and they can have many intersection points. And in our case, only the last intersection point matters. Since our proof heavily relies on understanding of these crossing points, intersection points, this is quite annoying. And what we did is we adjust the pricing function so that it satisfies some version of single crossing property without changing the outcome, and we still maintain this auxiliary pricing function is okay. To summarize, in this paper, we characterize the optimal deterministic mechanism for a value maximizer with private target and private values. We show that the optimal mechanism does not require target screening. And for future directions, it would be interesting to extend our result to more complicated settings, including randomized mechanisms, multiple buyers, and value maximizers with not only ROS constraint, but also budget constraint. Another direction for future work is to compare the second best characterized in this paper to the first best and see if some approximation response can be made. Lastly, we feel that our paper has pretty intuitive geometric understanding. However, we have some annoying proofs, and we think there's some hope to simplify the proof, especially the case analysis, by using some better mathematical tools. Thank you.